Now we are going to find the area under one arch of the cycloid. Now remember, I explained in the previous video, the cycloid takes this shape and the parametric representation of the cycloid is this one, right? So what they ask is to find the area under a one arch, that is the area from here to here, because all the other arches are identical to each other, right? Now, so basically what we have to do is, if we represent this as y, that means we have to find the area of the curve y, and since the horizontal axis is x, we are integrating with respect to x, and the 2 points are 0 and 2 pi r, right? 0 and 2 pi r. Okay, and now here it will be not easy to come up with the direct relationship between x and y. So what we should do is, we should do the integral according to these parametric representations. Simply we have to convert our integral this down. You can see that this is an integral in the x variable, so we have to convert the integral into a theta variable. And there's one more thing that I want to show you. Now remember, we formed this cycloid by rolling a circle of radius r. Okay, so now just by looking at this diagram, sometimes you might think that this area is kind of, sometimes you might tend to see that this looks like it's the half of the given circle. Now remember, we just roll a circle across this x-axis. So if you have a circle with radius r, what is the area of this circle? That is pi r squared. So sometimes you might think about this region as the half of the area of this circle, or sometimes you might think that it will also give the full area, right? But surprisingly, we can see that once you do the calculation, we can see that this is 3 times the area of this rotated circle. It's kind of a strange result. Okay, there's no way of visualizing it at the beginning, right? But I think Galileo, there was a famous mathematician called Galileo, and I think he have guessed that this arch should take 3 times pi r squared, but at that time he didn't have proper mathematical tools to prove this result. So on a later day, a different mathematician proved this one, because at the time of Galileo, all these integral techniques were not developed as of today, right? Okay, so anyway, now we saw that the given arch, the mentioned arch, this area will be given from this integral. Now see here, you have the upper limit of x-axis, right, which is pi r squared. Now we are going to convert everything into a theta variable. So let's start with this x coordinate, and that can be done like this, right? So we have this x relationship, and if we differentiate it with respect to theta, you have this one, so dx is equal to this one. So in our original equation, instead of this dx term, we can write down r minus r cos theta times dx d theta, right? R minus r cos theta times, it's not actually a multiplication, but anyway, we can replace dx with this term, right? And then how about y? For y we can directly use this one, 1 minus cos theta. And what about this lower and upper limits? Those two are some important things that you should clearly do the computation, or else you should have a good understanding about this picture in order to come up with these suitable lower and upper limits. The reason is, now for the lower limit, of course, you can try to evaluate the answer directly from this relationship, because when x is equal to 0, then this will be equal to 0. That means this is equal to 0, and you can cancel out r and you can have this one, right? So now from this equation, if you think carefully about the sine trigonometric function, this is the only possible way for theta to exist in order to satisfy this equation. Reason is, our theta value for this particular arch starting from 0 to 2 pi will vary from 0 to 2 pi. That means, in order to generate this arch, okay, the corresponding theta at this point will be equal to 0, and when theta increases, all these points will be generated, and then ultimately this curve reaches this end point when theta is equal to 2 pi, right? So with this knowledge, you can directly substitute for the lower and upper limits, right? Otherwise, if you are going to compute it through this equation, as we normally, that's the normal procedure of handling these integrals when you are doing the substitution. This is more or less similar to those substitution methods that we do in integrals, right? But here, if we are going to solve these equations, now even for this upper limit case, when x is equal to 2 pi r, then this will be r theta minus sine theta. So our equation will be equal to this one, right? In fact, it's sine theta is equal to theta minus 2 pi. So you can think about this equation through trigonometric relationships, like you can write sine theta as theta minus 2 pi and theta minus 2 pi. So if this, now as we are only dealing within this region, we can have theta minus 2 pi to be equal to 0. Like that, you can evaluate the suitable lower and upper endpoints through these relationships. But it's far more convenient to look at to have a understanding about this curve and the corresponding parametric values, right? So now we know that the curve is represented by this parametric equation, and we also saw that by changing the values of this parameter theta, you can have different x and y values. So the theory says that, now this is the first time that I'm going to say that theory. The theory says that when theta is equal to 0, we start from this point, and when theta increases, it goes like this, right? And then it comes back, maintaining this half circle nature, and at this end point theta reaches 2 pi, so the curve goes like this, right? And that means for this particular x value, that is x equals 0, this is the corresponding theta. And for this particular x value, see here you have a 2 pi r, okay? The corresponding theta is 2 pi, right? So it's not necessary to do all these calculations if we know the theta, or the the behavior of this parametric curve and the values or the corresponding values of the parameter theta, right? Now for that, of course, you need to have a good understanding about the nature of this curve. Without that, you won't be able to come up with all these relationships, right? So now remember, in the very first example in the previous video, we were easily able to compute the upper and lower limits corresponding to the new variable. But here it's not that easy if you just think about this equation only, right? Hence what we can do is we can go to the origin of this cycloid, and then there it says when theta is equal to 0, you have x equals 0, and it completes this one full cycle when theta is equal to 2 pi. So the corresponding lower and upper limits in terms of theta will be 0 and 2 pi. See, here you have a 2 pi r, but you don't have an r term in here when it is represented with respect to theta. Once you are done with this, it's just a matter of simplifying the integral. And when you do the calculation, you can see that things will be simplified a little further, and by applying the suitable these expansions, you can finally obtain that the value of the area is equal to 3 times pi r squared. Remember, the area of a circle with radius r is equal to pi r squared, okay? And you can see that the area of that single arch is equal to 3 times the area of the circle that was used to generate this cycloid, where r is the radius. So when you are doing these integrations and differentiations, it is treated as a constant, okay? Right.